the idea is that we consider all lambda terms as linear functions, homomorphic. So from the first point of view, we have, for example, the quantum lambda calculus, Peter Selinger and Benoit Valiron quantum lambda calculus as an example. Also, we have Van Tonder calculus. And as example of the second approach, we have, for example, Arrighi and Dweck lambda calculus. These are, in principle, two different ways to deal with the non-cloning property. So, in the first approach, the idea is to, as I say, to forbid this kind of terms, while in the second approach, the idea is to use distributivity or preservation of the operations and to delay the process, and at the end, we evaluate on the basis. That's the idea of the second approach. So each solution has its advantages. For example, for the first, if you want, for example, to implement the conditional if then else, the linear algebra approach is very convenient because, as I say, we use distributivity, and at the end, we can extend to vector spaces using the definition on the qubits, on the basis. However, if I want to interpret, for example, if I want to use or to have a term like measurement, for example, the linear algebra approach is not very convenient, so I will need, for example, a linear logic or other approach. So, the key point here is to consider the best of the two worlds. So, the idea is to define a type that is at the same time is linear and at the same time is a superposed type. So the idea is that base state can be cloned and superposed state cannot. So we distinguish in these two types in the language, and we get, as I said, the best of the two worlds. So the language that I will show you the categorical model is called lambda S, due to Alejandro Díaz-Caro and Gilles Dweck, and it's an extension of the lambda calculus that unifies these two approaches. The type system has a constructor, as I say, S, that it applies to every types, and the idea, the intuition is that SA is the span of A. So in some sense, SA is a basis, and SA is a linear combination of these bases. That's the intuition. Of course, this will be then put in categorical terms. Right? So let's compare with linear logic. In linear logic, all the types, in principle, are linear, and I have a symbol that they denote the bank A that say that these are the duplicable terms, that these are the terms that live in the classical world. But if I consider just the tape, in principle, this type is linear, so it's non-duplicable. In lambda S, instead, we do the opposite. All the terms, in principle, are basis for another type. So when we write when we write S, we are saying that this SA is in principle a non-clonable, so it's a linear type, a linear combination of the bases. So it's the opposite way. So in this talk, as I say, we are going to give a categorical semantic of the lambda S aster. So we are going not to consider the measurement. This is for future work, and we are going to show that the model is obtained by an adjunction between a Cartesian closed category and a monoidal closed category that is additive also. Okay, let's talk about some background. There is the algebraic lambda calculi due to Lionel Vaux, which is a restriction of the differential lambda calculus that uses this notion of linear combination of programs, but without differential operator. There is also the linear algebraic lambda calculus due to Arregui and Dowet. This was meant for quantum computation, and it has a rewrite system that describes basically the law of the linear algebra. This was inspired by Nu and Bendix, and they adapt this idea to linear algebra computation. So we take this on the calculus. So what about models of linear algebra or linear logic? So basically, models of linear logic are interpret the bank as a comonad, right? As a monoidal comonad. For example, there is the Seeley models, Robert Seeley models, Lafont models, Highland models. All these models do the same job. They consider a comonoidal monad and interpret the bank as a comonad. But there is also another categorical model due to Nick Benton, which instead of considering a comonad, he considered a monoidal junction, so it's more basic, and then he built the comonad. So we are very close to this model, but instead of consider the comonad, we are going to consider the monad of this construction, right? And the idea is that we are going to interpret the S constructor as the monad, U composed with S, right? So our model is not from the point of view of the monoidal category, but from the point of view of the Cartesian category. So we see all the constructions are from the point of view of the classic world. And the idea is to use these maps. These are the maps that come with the monoidal junction, and all the calculations are done in the same way. So we go to the monoidal structure, we do computations, and we return to the classic world, right? This is the idea of all the computations in this paper. And this is completely different from linear logic, from models of linear logic, which are all the operations are done in the monoidal structure. For example, the product is defined using tensor and the comonad, right? So now the lambda S language. So we define the lambda S Aster language, which, as I say, is the lambda S without measurement. So we are going to give the terms and types. So we have basic types, and we have S, this type, which is linear combinations. We have product without homes. We have a constant for the qubits, lambda abstractions. We have a notion of sum, zero, product with scalars. And we have tails, head. We have products, and we have two notions of casting, right and left casting. And the intuition of this language is very clear. The idea is that B is for the basis, is the Boolean type. The idea of SB is the linear combination of the basis, as I say. Also, there are, for example, linear combination of functions, etc., etc. So the syntax of the term contains lambda abstraction, as every lambda calculus. Two terms. We have also a sum, a scalar multiplication. We have in lambda S a structure which is the measurement, but we are not considering this calculus. And two casting operations. This is what they say. Here is an example that explains the casting. So the casting is something that permits us to distribute, even though we are in a Cartesian category. That's the idea of the casting. So we have a rewrite system that has basically two strategies, a can by name strategy and can by basis strategy. The can by name strategy is when we apply in a type like this, the quantum types, and a call by name strategy is when we apply to a basis type. So the idea is, okay, we distribute first, and then we apply to the basis. Here's an example. Okay, first we check if it is world type using some rules that I will define, and then we reduce it using the call by base strategy. So we reduce, for example, this term, we apply to this, we distribute, and then we apply to the basis. The type relation is given in the next figure. So here's the rules for types. There is a, I don't know if it's clear, it's head and tail, castings, and the right relates, as I say, to the strategies. Okay, there is a rewrite system that is basically are applying the rules of the linear algebra or the properties of a linear algebra. More rules for the if then else. More rules for the axioms. So here we are inspired on this language, a rigid way. The next figure we implement the casting. A lot of rules. I skip this. I go more rules for the reduction. Okay, and some theorems. Confluent of linear means that linear is confluent. Linear is the name of this language. So substitution reduction is true also on closed terms, and strong normalization. And now it comes the categorical construction for this language. So as I say, the idea is to consider the inspiration of this Nick Benton model, but as I say, we consider not this part, but this part. So we have an adjunction for algebraic manipulation. It's a monoidal adjunction where C is a Cartesian closed category with a terminal object. The category, this is a symmetric monoidal closed category, but also is an additive category that satisfies two axioms. An absorption axiom that says that all of this diagonal commute, where 0 is the zero morphing of the additive category, and a distributive axiom that says that this diagram always commute, where this D is for duplication in the Cartesian category, N is for the monoidal structure, the structural map of the monoidal structure, D is for the preservation of the tensor, and P is for the preservation of the product. Here are the explicit map, and I have an object in the category that satisfies an universal property. This is part of the definition. It's part of the definition. So for every f and g, this diagram commute. Well, as I say, of course, B interprets the type, the Boolean type. I need the clarification from the product and the fact that it's a monoidal close, a Cartesian category, a Cartesian closed category, and I use that junction, that the monad defined by the adjunction. Okay, I need the axiom, the absorption map axiom says that this map, this commutes for every object, not just for the objects that are in the image of U. That's a remark. And now it comes the denotation semantics. So, of course, everything is clear. As I say, the objects B interpret the type B, the home is clear. The SA is interpreted by the monad, as I say. The product interprets the product of the language. The map sum is defined using the nabla that give us this construction. So the idea is that we use the preservation of the product, and the casting is defined as follows. So we use the mediating arrow of the monad and the structural map of the adjunction. So this is the basic level of the casting, and then we extend to all the levels that we can reach in the language. We generalize this, and okay, skip that. And now it comes the notation semantics. The axioms are interpreted as this is the terminal object. You use the injections for the objects, 0 and 1, and we use the scalars. We go to the monoidal structure. We use the tensor. We return to the Cartesian category for the scalars. The same for the sum, using the map that I defined previously. And everything is very standard here. And okay, some properties of this denotation semantic. It's sound and complete. It satisfies independence of the derivation. So if you have two different derivations, the meaning is the same. It satisfies a substitution lemma, which is a technical lemma to prove the soundness. And in order to prove completeness, we adapt a Thales proof for strong normalization. And we prove also adequacy and completeness. So at the end, we get the model, the categorical model for this lambda S. And for future work, we have to deal with this measurement in the language and the model, in the model. And that's all. So if
questions for Octavio? I have one.
yeah.
So there were a lot of rules
Yes.
in this talk.
Very.
Is there any hope for sort of unifying them or condensing them and somehow making it, I don't know, a little easier to grasp in a smaller number of bytes?
I have no idea. Because linear algebra need a lot of axioms, so we need a lot of rules. So that's the problem.
Other questions? All right, let's thank our speaker again. We need the microphone.
Oh, sorry.
Okay, I forgot to give it to the speaker before this. So
Well,
we're doing all right.
I forgot to look at the time, and the people I was having lunch with didn't really intend on attending the talk, so.
What?
Nothing. Let's leave.
All right.
Thanks.
So we're going to go a little more linear and nonlinear type theory. So Vladimir is going to tell us about mixed linear and nonlinear recursive types.
Yeah, thanks. So this is joint work with Mike Mislove and Bert Lindenhovius from Tulane in New Orleans. Yeah, so well, again, I was talking about linear and nonlinear type systems, but this one here, this talk is more general. So the previous one was about quantum programming, whereas this one is just a generic linear nonlinear type system. So these kind of type systems have found applications in concurrency, in quantum programming, as I talked about. So in particular in concurrency, there's a typing discipline for the P calculus called session types. There's also application in circuit description languages where they could be used to talk about Petri nets and other string diagrammatic theories like that. In general, linear types can also be used in classical programming to program with resource-sensitive data. Okay, so the question is, how do you add recursive types to such a type system? So in the previous talk, I was talking about inductive data types, which is considerably easier than recursive data types, because when you have recursive data types, you have more structure, and you end up with being able to perform full-blown type recursion, which then induces term recursion. So things are in general more complicated. So in this paper, we've solved the issue, and we've explained everything in a lot of detail as to how you can do it. So the paper is it's available in the archive, 60 pages. Everything is explained in excruciating detail. Some of the proofs are pretty big, so everything's there. And I'll talk about it at ICFP. So ICFP is the International Conference on Functional Programming, which is in Berlin this year, and I'll present the paper there. Okay, so in particular, the main contributions are a new technique for solving domain equations within the category CPO, which is needed in order to describe the comonoid structure of the recursive types. We present also some coherence theorems for parameterized initial algebras, and we also present sound and adequate categorical models, which are both abstract and also a lot of concrete models as well. Okay, so long story short, the syntax and the operation of semantics is based on mostly prior work. So there's a paper by Peter Selinger and Francisco Rios, and there's another Lix paper. So you can read any one of them, but I recommend the second one. So yeah, this is the syntax is based on this. Anyway, so the hard stuff is denotational semantics. So how can you do everything there, basically? So in particular, let's say you have a quantum programming language, then you want the list of qubits to be linear, so that you don't accidentally copy something and then break quantum mechanics. Or if you have a bunch of file handlers, then you also want like a list of file handlers to also be linear, so that if you copy it, then you have two file handlers pointing to the same type, and it just becomes a mess. So you don't want that. But on the other hand, if you have a list of natural numbers, let's say, so this is just standard classical information, then you should be able to copy it as you please. And in particular, here I want to focus on the word implicitly. So that is, can you actually do this in an intelligent way without slapping a bang on everything? So this is the linear logic approach of copying and deletion. Requires using a lot of bangs, and this is it's very annoying if you actually want to program with this. So being able to eliminate the bang as much as possible is worth considering. And here, we show how you can do this implicitly without the bang to a large extent. Okay, so the gold standard for recursive types is basically a language called FPC, which is the fixed point calculus. So it's described by Gordon Plotkin and Marcel Fiori. And the question that we also want to address here is how would you design a linear nonlinear version of FPC? Like, what is an LNL-FPC? Okay, so well, this is what it is basically. So it's the syntax, a part of it. So I'll just briefly go through some of the main constructs here. So we have type variables, which we need to form recursive types. We have term variables, which they're just range over terms. Now the type structure is given by the following grammar here. So we have type variables x, which are what you have to. This is how you can form open types. Now the types are closed under sums, pairs, function space, and we also have the bank here. So I need the bank in order to take care of lambda abstractions and the like. And this is the operator which we use to form recursive types. Now a subset of my types are the nonlinear types. So these are the types that I can copy and discard at will. So without having to throw in any bangs or anything like that. And they're exactly the same as the above line, except that function space cannot be a top-level construct. So if you want to have a function space, then you have to hide it behind the bank here. Okay, and then you can copy and delete. All right, so we have type context. So this is a formality which you need in order to form recursive types, and we have just standard term contexts, and we also have nonlinear term contexts, which are just the same as before, but the types have to be nonlinear. So the terms of the language are also pretty standard. We have variables, we have left and right for conditional, and also a case construction for conditional branching and for pattern matching. We have pairs. This is the introduction rule. This is the elimination rule for pairing. Lambda abstractions. This is an application to a lambda abstraction. We have lift and force, which comes from the structure of intuitionistic linear logic. So in particular, if you can lift a term, it means that the term M contains no free variables, and you can therefore copy it and delete it. And it also serves another purpose. The lift here actually is used also to thunk computations. So if you slap a lift in front of a program, it means that you defer the evaluation there. And on this basis, you can encode things like streams. And the force is the elimination rule for the bank type, which means that if you have previously lifted something, now if you force it, you can just continue execute. And we have fold and unfold, which are the introduction and elimination rules for recursive types. And the values of the language are perfectly standard. So the values are the things which you can actually compute. So this is where termination stops. Okay, my operational semantics, they're in blue. I don't know why. I copied it from my paper, but it just became blue for some reason. They're completely standard, so I don't want to talk about this either. So I just included it for completeness. Okay, so some derived programs. So I was asked to focus more on the programming side here. And actually, if you go back to the minimum syntax here, it's actually not obvious how you can even write any program here. So I mean, for example, what is a base type here? It's not immediately obvious. So how would you even write any program here? So it's actually not a bad exercise to do, but I'll tell you immediately because we don't have time for exercises. So the first type that you can define is actually the empty type. Okay, it's called empty because you will never be able to define a program of this type. And you define it by saying that the empty type is equal to mu(x) dot x. So categorically, you can see that this makes sense because mu(x) dot x is essentially it's interpreted as the initial algebra of the identity functor, which is the initial object, and in our case, the initial object is actually a zero object. Okay, so once you do this, now you can define the unit type, which I've written here with an I as a shorthand for a tensor unit, which is equal to bang of 0 lollipop 0. And now with the unit type, you can now actually write a program, and this is the first program that you can possibly write in the language, which is very simple, which is called star, and this is the canonical value of unit type, and you do it by just lifting the lambda abstraction of type by lifting the identity on the empty type. Okay, so this is what you can do. And well, now using these simple constructs, you can now define more complicated types. So for example, the first, I would say, non-trivial type that you can define is, well, the first non-trivial inductive type is the type of natural numbers, which is defined in the following standard way here. And this is a nonlinear type. So all the constructs so far have been nonlinear. So to give you an example, the zero natural number is defined by taking the star program, like defined above, then taking a left injection into, well, I plus nat, and then folding this. Okay, and this is actually a canonical definition of the zero natural number. It's exactly the same in FPC. So the successor function, is well, it's a function from a natural number to a natural number. It's defined in the following way. So given a natural number, you take the right injection of the natural number into I plus nat, you fold it, and this is actually the next one. Okay, so this is a canonical definition of the successor function. Lists of natural numbers are defined again in a pretty standard way. This is now a nonlinear type, and it's nonlinear because all of the information here is nonlinear. But if you want to define a list of qubits, now this becomes according to the grammar that I showed you previously, this is now a linear type. Well, because we see that like a qubit appears here, which is a linear type. And since now we have the ability to also form type expressions involving the bang, you can now also encode streams. Okay, so in the previous talk I was talking about, I didn't have a bang, and all the inductive data types were finite. Whereas now here you can talk about infinite data types such as streams by using the bang, which then allows you to make non-terminating computations, which you can hide behind the lift, which has the effect of deferring the evaluation, and that's linear. Okay, so we can define some useful data structures, as we saw in the previous slide. But the minimum syntax also allows you to do some crazy stuff. In particular, type level recursion here induces term level recursion. Right? So this is a well-known result in FPC. And well, obviously, if we didn't recreate it here, then we haven't really, we're just not doing anything. So there's a theorem which in the paper which explains how we can derive a recursion operator. And moreover, our recursion operator is also exactly the same as the one that we talked about in LIX last year. So this is not meant to be human readable, but it shows that with the very basic syntax that we have, you can do some very complicated things, and you can define a recursion operator which looks like this. So that is given some recursive function of the type bang of whatever. Then you can this is the name of the function. You have a function body which can then depend on the recursion. Then this is something which you can interpret. So I'll give you an example. So a factorial function. So this is how you would write it in the formal syntax. Now in an actual implementation of the language, you should use some syntactic sugar. But here I wanted to emphasize to show you how the formal syntax looks like, because I think it's actually not that bad. It's actually, I think, kind of close to a standard nonlinear syntax. So anyway, going through the function line by line, what I'm saying here is that I define a recursive function called factorial, which, given a natural number n, does the following. Now the first thing is to do a pattern match on the natural number. So that is, I want to see if it's 0 or if it's not 0. Okay, so I unfold it, I do a pattern match, and then I see if in the left case that's the left injection, which means it's just a fancy way of saying that you have 0. Well, in this case I return the successor of 0, which is 1, because 0 factorial is 1. And otherwise I know it's not 0, and in this case I would, well, technically I have to define what a multiplication function is, but whatever, you can do it. And then you multiply n with the result of the recursive call evaluated at n prime, which is n minus 1. Okay, and now the only linear construct here is this force, which well, it's a technicality that comes from dealing with banks, which you have to carry around here. But perhaps there's something which could be ameliorated if you use some syntactic sugar. Well, in any case, an important note here is that we have implicit rules for copying and discarding. So in particular, you see that I use the variable n here once, but I also use it here. So if you actually use the obvious translation of linear logic under a Curry-Howard interpretation, then you have to now specifically say copy n as n prime, n double prime, and so on, and then you just do all these things. Whereas our type system has implicit rules for copying, so we don't have to borrow with these kind of things. The only things that you have to borrow with is the force and the lift, basically. Okay, so going towards the denotational interpretation, there's a few things that are important here. The first one is the notion of an omega category, which is introduced by Lemon and Smith in the 1980s. So an omega category is just a category which has omega co-limits, and it has an initial object. So it means that there you can compute initial algebras. And the functors which behave well in these categories are the omega functors, which are functors that preserve omega co-limits. Okay, and these, well, the omega categories, they're closed under formation of function categories, and they satisfy some nice properties, which I'm not going to tell you about here, but basically they're very good for computing parameterized initial algebras. So here, to interpret these kinds of inductive data types, you don't need just an initial algebra. You need a slightly stronger notion, which is called a parameterized initial algebra. And this is because you have to be able to talk about mutual induction or mutual recursion of types. Okay, so here I'm giving you the baby's version of a parameterized initial algebra. So it's not complete, but it carries the main essential information. Okay, so if you have some omega category B and you have a functor, this you should read as an endo functor on B, which is parameterized by A. So this is the parameterization part here. Well, then the parameterized initial algebra consists of a functor which, well, given something from A, gets you an object in B. I call this, well, T dagger. This is the usual notation people in the literature use for this. And now you also need a natural isomorphism phi, such that basically the pair is characterized by the property that T dagger of A and phi of A is the initial TA blank algebra. So if you, I mean, obviously TA blank is now an endo functor on B. So you can now talk about initial algebras. And what you're saying is that this whole parameterization by the category A just makes sense. Okay. Yeah, so you got to prove a bunch of theorems. Well, I'm not going to show you what they are, but there's some important coherence conditions which you have to make sure hold. Well, one of the most important ones is that if you're given a natural isomorphism A of this shape here, then you also need to define, you also have to extend the dagger mapping to natural isomorphisms as well. Because then this is something that we exploit for the construction of comonoids later on. All right, so this is a little technical, but it's taken care of. All right, so the next step in the semantics is to well, recall an important result from Smith and Plotkin. This is Smith and Plotkin 1982. It's a very famous paper where they introduced the limit co-limit coincidence. So anyway, some background before that. So if you have a CPU enriched category or a DCPO enriched category, it doesn't matter, then the subcategory of embeddings is denoted with CE. And this is the category where all of the morphisms are embeddings in the EP sense, in the embedding projection sense. And now they have observed, so this is actually one of the theorems in that paper which is not that famous. It's not the main result, but it's actually very useful for us because it allows you to see a mixed variance functor like of this shape as a covariant functor by just redefining its action on morphisms in a nice way. So in particular, if you do this, you can see it as a covariant functor on the subcategories of embeddings, which has the same action on objects, but its action on morphisms is well, it's a little different because here you have to take the corresponding projection of the morphism. So the projection gives you an involution on the category. And then in this case, what happens is that if you do this, then this functor TE actually automatically becomes an omega functor. And therefore, you can now start talking about initial algebras and so on like quite easy. And this is actually, so I included a remark here saying that I'm not aware of any papers, even though, I mean, this has been known for a very long time. I'm not actually aware of any papers which use this as the base for type interpretation. Now, people usually use some derivations of this result, but this exact result I've never seen in any paper. But we use it here, and this is something which I think simplifies the semantics quite a bit. Okay, so since it's a linear nonlinear language, well, obviously we got to talk about intuitionistic linear logic, and the model of intuitionistic linear logic that we use in this paper was presented by Nick Benton in '94. And I think it's a very beautiful model because it's very, the data is very small, it's very compact. It's just given by a Cartesian closed category C, which has finite coproducts. So this is where you interpret all of the nonlinear information. You also need a symmetric model closed category with coproducts where you interpret the linear judgments. And you also need a symmetric model adjunction between them, which basically preserves all of the structure that you care about. Okay, so now it's our notion of a model. So to model LNL-FPC, we also obviously have a model of intuitionistic linear logic, but we need to add some additional structure to so that we're able to interpret the recursive types. So the data is now given by the following structure. So again, we assume that we have a symmetric model closed category here, but we also require that all of the structure is enriched over CPOs. Now, the other requirements are that we have an initial object such that the initial morphisms are embeddings in the domain theoretic sense. And we assume co-limits over these embeddings so that we can form some initial algebras in there. we also assume that coproducts respect the CPO structure. Okay, so that's the assumption on the linear part. And the next assumption is that we have an adjunction where, well, the left category has to be CPO. We don't know how to abstract away from this, so we don't know if this could be replaced by something else. That's future work. So we assume that the Cartesian category is fixed, it's CPO, and then we assume that we have a symmetric model adjunction between the two categories. Now in this case, it's actually not obvious, but you can prove that the initial object is in fact a zero object, and that the zero morphisms are least. So this means that the category is actually enriched over pointed CPOs with strict maps. And well, the second point is pretty important. It means that you can solve all recursive domain equations that you want there in the usual sense. Anyway, there's a proof in the paper about this. But okay, so here this says that I can solve all the recursive domain equations I want in L. But because I also mentioned that I want to be able to implicitly copy and discard recursive types without having to borrow with bangs and the like, the way that you can accomplish this is by also solving some recursive domain equations in here. In particular, I have to be able to solve recursive domain equations in CPO in a certain for the nonlinear types. And this is difficult because the existing approaches don't really tell you how you can do that. So we had to introduce a new technique for solving recursive domain equations. And yeah, so this took a bit of work, but it's based on the following ideas. So if you take a CPO functor, then between two CPO categories, then we say that the morphism is a pre-embedding if it maps to an embedding in the other category. So essentially, it's a reflection, argument here. Okay, and in a specific case for the model, we should say that the subcategory of CPOs and pre-embeddings, we will denote it in this way, and it's defined to be the subcategory where all of the morphisms are pre-embeddings with respect to the left adjoint. Okay, so this is fixed for the model. So recall that the left adjoint here is I just indicate as F. Okay, so this defines now a subcategory of CPO. Now this is important because when you compute initial algebras in CPO, you always start by considering some initial map from the initial object into something else. And now the initial map is not an embedding because there is no map going in the other way in CPO. However, it is actually a pre-embedding with it's pre-embedding in the sense that I just explained. And now we have observed that the category of pre-embeddings is actually very well behaved, and it has all the structure that you need in order to interpret recursive types within it. Okay, so there's another theorem which says that so the first bullet point here is, I mean, most of it was known by other results, but you can prove that the subcategory of embeddings on the linear side is an omega category, and that this part here says that co-limits are computed in exactly the same way as in the ambient category L. Okay, so it's not that difficult. The second observation is important, which says that the subcategory of pre-embeddings also enjoys exactly the same property. So it's an omega category with co-limits computed in the same way as in the ambient category. And well, the proof here is actually also pretty easy. It's not difficult to prove, but it was not easy to observe. So once you ask the question, then it becomes obvious. Okay, and then we prove a bunch of other theorems here, which show that actually you should prove all the types in the subcategory of pre-embeddings on the Cartesian side, and in the subcategory of embeddings on the linear side. So there's a bunch of other theorems which I'm not going to say here. And also we use this trick which allows us to turn mixed variance functors into covariant functors using the observation of Smith and Plotkin. And yeah, so this is these are the main categorical observations that you need. And now some concrete models. All right, so we've done some work on identifying some concrete models. So I'll tell you everything we know. So the simplest non-trivial one is given by the adjunction between CPO, which I've talked about, and then this is the category of CPOs with pointed CPOs with strict maps. And the left adjoint here is just lifting, right adjoint is forgetful functor. So this is both categories here well known. They're very important in semantics, and we're actually pretty happy with this one because this is a very simple model. And we like the fact that we have simple models for our language. It just shows that our constructions are reasonable. Now, slightly more complicated models that are based on Presheaves. Okay, so here we have a class of models, and then I'll show you by instantiating this category M. On the next slide, I'll show you some concrete ones which have been used in other domains. Okay, so if you're given a symmetric model category, which has to be small, now this is very important because if it's not small, then you end up with foundational issues here. You break set theory. Anyway, so you take this, you take then the free CPO bottom strict enrichment, which is the fancy way of saying that you freely add the least element everywhere. To every home set you add a least element. To every home set you add you freely add the least element. Sorry, and then you take the enriched uneda embedding. Okay, so it exists. It's pretty much the same as the normal one, but you just have to take enriched functors instead. Okay, so in this case, you can now compose two adjunctions. So the first one is the nice one from the previous slide, and this is now a co-power adjunction. So there is a book by Francis Bourseau who explains that, yeah, this always exists, and it's like a general fact in the rich category theory. So this is a co-power / power adjunction here. All right, and this is now a CPO LNL model in the sense that we have. Okay, so if the category M, so this is now by instantiating the category M, you can now obtain concrete models which have been used in some settings. So the first one is the first one is basically a quantum model. So if you take the prop where the morphisms are the n by n complex matrices, then you get a model for quantum programming. Okay, so then you're talking about Presheaves over finite dimensional Hilbert spaces. Okay, it's a quantum programming model. Such Presheaves models have been used to study quantum programming in general. So there are other papers which have done this. Okay, if you want to talk about ZX diagrams or whatever, just take some free category of ZX diagrams, and then you get a circuit description language where you build ZX diagrams. If you want to talk about Petri nets with boundary, so there's a thesis by Owen Stevens where he shows it's a small symmetric model category. Then you get a programming language, you get a circuit description language which you can use to generate Petri nets and the like. And in general, you can also take some other free category of some string diagrammatic theory to talk about them. All right, so a conjectured model. So this one we're not really sure about. So one of the reviewers at ICFP suggested that we can check out Kegelspitzen, I can't say, models. So this is a notion introduced by Kimo and Plotkin, which is used for probabilistic computing. And so Mike actually looked into this, and well, basically there's several papers, but there's some issues there, and in general he suspects it will work, but he thinks it will involve a lot of work to prove all the relevant theorems and so on. But anyway, we conjecture it's okay. Oh yeah, also Mike discussed this with Goran Plotkin. What? Mike discussed this with Goran Plotkin as well, and he said it's probably fine. I don't know what's going on here. This is not behaving well. Sorry. Okay. Interpretation of types. Okay, so this is like a little non-standard here, but you gotta do two kinds of type interpretations. So first one is the standard one, which you interpret types as certain kinds of functors on the linear category. And as a special case, you conclude that the interpretation of a closed type is just an object of the subcategory of embeddings, which is exactly the same set as the objects of the linear category. So that's good. However, this doesn't explain how you can construct the comonoids that you need. And now, so this is the same as in the previous talk that I gave. So this is the idea is to provide a nonlinear interpretation for the nonlinear types. Now, in this case, we see those as functors on the subcategory of pre-embeddings. And as a special case, we therefore obtain that the interpretation of a closed nonlinear type is an object of CPO. But now the objects of CPO, they live in the Cartesian category, so every such object has a canonical comonoid structure. All right? So since we know what is the comonoid structure of this type, we can then use the left adjoint to import it into the linear category. And now we have by doing this, we now have a canonical comonoid structure in there, because the left adjoint is actually a strong monoidal functor, so preserves comonoids. Basically, that's the main idea. But in order to prove this, in order to prove that such an isomorphism exists here, you have to do a lot of work. And it's okay. So this is how we do the interpretation of types. I don't think I have time to cover this, but it's pretty standard. The only thing that you have to do here is to take the Smith and Plotkin trick, where you turn everything into a covariant functor on this side. Everything else is standard. And we essentially do the same thing on the nonlinear side as well. Okay, so to prove that this isomorphism between the standard interpretation and the nonlinear interpretation is coherent, you have to prove another theorem which looks like this. So that's actually it's pretty big proof. You have to do a lot of other coherence conditions on the categorical side. But you prove it, and then you stop caring about it because you get this corollary, which gives you everything that you need. And the corollary tells you that standard interpretation is basically the same as slapping the left adjoint to something which is Cartesian. And now, oh yeah, so another technicality here which I wanted to point out is that because we provide different kinds of type interpretations, now the semantic treatment is more complicated, because you have to formulate 3 substitution lemmas on types, like one for the standard interpretation, one for the nonlinear interpretation, but then you also need one for the natural isomorphism which relates the two, which is also defined by induction on the derivation of types. Okay, so it's more complicated than the usual one, which just has one like lemma. And in this case, we also need 2 kinds of folding and unfolding maps for the recursive types. One for the standard one, and also one for the nonlinear one. And then, well, you have to prove that this actually, they're nicely related to each other by showing that this diagram here can use. But anyway, so you do this, and now you can finally define, copying and discarding. And well, you have this box here, which is for the bang, but it's not that important. So anyway, the way you do it is you use, so if you have some nonlinear object here, or a nonlinear context, you use the isomorphism in order to rewrite it in this shape, to this form here. So this is now this now lives in the Cartesian category. So you can now take the terminal map, and here you have a canonical isomorphism given by the adjunction. For copying, it's essentially the same idea. You go into the nice form, and now you use the diagonal of the Cartesian category, and this is now given. So this isomorphism here is again given by the adjunction, and then you do the inverse isomorphism of the one that we constructed over there, and you've now copied what you had to copy in a canonical way. Okay, and this is used for promotion, or for lifting in the linear logical sense. And you can prove that actually this is now a co-commutative comonoid. We're done. Okay, so for the interpretation of terms, well, this is overall pretty easy now. I mean, the hard part was doing the interpretation of types. The interpretation of terms is pretty standard. You don't have to think too much. The only technicality which is left is to observe that to prove soundness, the values have to satisfy further properties. In particular, you have to prove that they're actually comonoid homomorphisms with respect to the comonoids that I described. But this is true, and the way you do it is by providing, again, a nonlinear interpretation within the Cartesian category CPU. Okay, then you prove soundness, which is standard, and we also prove computational adequacy. Now, in this case, reduction semantics is it's classical, completely deterministic. So the adequacy formulation is much simpler to state. So here it says that a program will terminate if and only if its interpretation is not the zero morphism. Okay, that's it. But this is true under some additional axioms. So you have to rule out the degenerate models here. Yeah, and the proof is like 20 pages of this. Anyway. Okay, well, I'm basically done. So to conclude, we introduce LNL-FPC. It's the linear nonlinear version of FPC, which is a well-known type system for talking about recursive types. Our type system is equipped with implicit weakening and contraction rules, which means that we can copy and delete without having to slap banks like all over the place, which is, I think, nice. And we explain how this can be modeled and so on. We established some new results about parameterized initial algebras. If somebody else wants to, I don't know, do something with initial algebras, do some inductive types, this could be useful. In particular, I used this in the previous paper that I talked about. So, I mean, I found it useful, but I don't know if other people will. We described a new technique for solving recursive domain equations in CPO, which is, I think, probably the main contribution of the paper here. And yeah, we just explained how you can take care of recursive types. And as future work, we would like to see if it's possible to remove CPO from the model. Currently, it's built in, it's baked in. It's unclear how this can be done. But this would be nice to do if possible. And the other question is, are there more concrete models? We don't know. It would be good to see if that's the case. I mentioned all of the ones that I know. So yeah, if anybody has some ideas, we'll appreciate it. So thanks.
We have time for just one or two questions.